What's up, guys? It's Mr. Brengle, and today I'm going to be going over the Force, Mass, and Acceleration Virtual Lab. I'm not going to go over much of the data collection. The instructions are in the instructions. Follow the steps. You will need to click on this link here that will take you to this website where you will actually perform your experiment. So you'll follow that along, and basically what I'm going to do is I'm going to go into my data sheet here where I have some mock data, and I'm going to show you how to get all of the things that you need, how to make your graphs, how to linearize, and then I'm going to talk about the lab report and the meaning of a lot of the stuff down here, the analysis stuff. I want to make sure that everybody understands what we're getting at here. Okay, so the first thing I went through and all I did was one trial, and this is actually, I'm glad this happened. I'm going to show you what happens when you don't do enough trials. Sometimes your data doesn't come out exactly the way that it should. So the first thing here, once you have your average time, we need to calculate the acceleration of the object, and you will need to go back to the instructions. It talks about this down here, step 9, calculating the acceleration. It gives you the equation that you need to use, and that is the equation from our acceleration unit. The change in position is equal to, what it's left out is the initial velocity times the time plus 1/2 at squared. And it left that out because the initial velocity of the object is 0. So if we come back over here and we're trying to put this in, remember, so it is delta x is equal to, let's write it like this. Instead of 1/2 at squared, let's write at squared over 2 because we're trying to solve for the acceleration. So if we do that, multiply by 2 on each side. Okay, so now we have 2 delta x is equal to the acceleration times the time squared. We now need to divide by time squared to get that out of here. Divide by time squared, and you can see that to find the acceleration, it's going to have to be 2 times your change in position over the time squared. So what we want to do is we want to put an equation in over here. Get back to my mouse. We want to put an equation in over here and let Google Sheets do the work for us. So to put this equation, I'm going to put equals, and then in parentheses, I'm going to put 2. And here's the thing. Your change in position is 1 meter every time. So, I mean, you can put 2 times 1, but you don't really need to because 2 times 1 is 2. So you can just do 2 divided by, click on your average time, and then use the caret and a 2 right there to square the values. And you just hit enter, and that is that's all you have to do. I'm going to zoom in here a little bit for you guys. So I'm going to go ahead and get rid of this equation stuff here since we've already gone over that. Once you have your acceleration for the first object, since you put that equation in there, all you have to do is drag it down, and it's going to fill in all those accelerations for you. Okay. The next step is to make your graph. So we're going to highlight everything. Okay. We're going to hit the chart button, or you can go to insert and then chart right here. It's been a minute since we've done this, so and it has populated a graph for me, and I just want to make sure that everything on this is correct. So let's take a look here. We always want to go to the setup. We want to make sure we have a scatter plot, which we do. We want these 2 boxes down here checked, which they are. We'll go to customize. We want to check our chart and axis titles. In the title, I do not need the units, so it should just say acceleration versus mass. And on the horizontal and vertical axes, we do want the units, so mass in kilograms and acceleration in meters per second. Let's get a caret in there squared. And the reason it didn't have that caret in there is if you actually look back over here, I did not put it in right there. So we'll add that in. Okay, go back to this. So we'll continue on here. We'll go ahead and go to series. And then we're going to scroll down, and normally we would add a trend line. I'm just showing you this, but since this is a curved graph, we don't need a trend line. We don't really need an equation because we can't do much with that. If you prefer to have the trend line on there, you can, but it is not necessary for the for the curved graph, and it doesn't look very good anyway, so I'm probably just going to take mine off. So we've got a hyperbola here. Okay, we need to linearize that. So if you guys remember, the equation for this graph is y equals 1 over x. The reason for that is as x increases, y decreases. So if you think about that equation, so y equals 1 over x. If you increase the x value, that will decrease y, which is what's happening over here. You're increasing here on x, and y decreases. Okay? So to linearize this, we need to graph y versus 1 over x. So remember, this is your y column right here. This is x. Or I'm sorry, other way around. Sorry. This is x, this is y. So acceleration will be on our y-axis. Okay, so we want to do 1 over mass, and when we do that, we're actually going to write 1 over mass, and then we also need to put 1 over kilograms for the units. Okay, and then we'll just leave, in fact, we can just copy and paste our acceleration in there. Okay, so the acceleration values, you can just hit the equal sign and click on acceleration over here, hit enter, and then you can drag this down and fill in all those values. Now for the mass, we need to enter an equation because it's no longer just mass. It's equal sign 1 divided by, and then click on your mass, hit enter. It will do 1 divided by that initial mass number, and now we have 1 divided by all of our masses here. Okay, so we now have our second graph. If you're following along with the lab report, the first data table goes right in here. So that's the big one. That would be this one right here. Okay. The data table B, the accelerations for different masses, would be this one right here. Okay. And then you're going to put your I actually don't know that I have. Yes, I do. Modify your graph and paste it below. So I want you to put your graphs in. Put both of them in, even though I don't think I explicitly state that. But so now we're going to look at some of these questions here. It says, what is the shape of your acceleration versus mass graph? So that's this one here. This is a hyperbola. Okay. The relationship is inverse, because remember that skateboarder is going down, and then he goes into the loop, and he gets inverted, and he goes out. And then this is where now we're caught up, and we need to look at our linear graph, which should come from graphing this data over here. So we'll go ahead and hit Insert Chart. And you can see that mine is not perfectly linear. So let's see what we can do about that. We've got Setup, Scatter Chart. We've got these two checked. We go over to Customize. Always check your horizontal axis to make sure that neither of these boxes are checked. If only one of those boxes is showing up, the other one isn't, there is something wrong, and you just need to basically delete all of this data and just do it again, and usually that fixes it. Our chart title, we want to get rid of the units. We don't need those in our chart title. Get rid of that. And then it looks like our horizontal axis and our vertical axis are fine. So we'll go ahead and move on and click on Series. And then we're going to go to trend line. We want that to be linear, and I want to show the r-squared value. Now, I'm going to show you the difference here. If I click on polynomial, it actually goes to a 0.999 r-squared value, and it looks like it's a Groot graph. It is supposed to be linear, and 0.959, so basically 0.96, that is a good r-squared value. Sometimes you're just going to get a shape that works for both, but this is supposed to be linear. And if you look at our scaling here, it's only going up to 5, so these differences are really not that big. If we had a little bit different data, if I had done more trials, then it'd probably be a little bit straighter. But this is a fine r-squared value. We want to go over here to Label. Instead of Custom, click Use Equation. This puts the equation right here on there for us. And just don't get confused, that r-squared value is not part of that equation. So you really don't have to put the r-squared value on there. You need the equation though. However, this lets me know that you are indeed looking at this to make sure you have the right shape. So this is our next graph. So we're going to go back over here. to our lab report, and you're going to paste that graph in right here under number 4. Once you have a linear graph, add the equation, which we just did, and now is the bulk of this, what's important here, the units for slope, what does the slope represent, and what's the physics equation. So I'm going to zoom in a little bit on this too. Okay, so I'm going to do all of this right underneath it. So we're going to be looking at these right here. Okay, so the units of our slope, remember, we just did it was acceleration versus 1 over mass. Okay, we got this straight line here. So if we were looking at units for the slope, let's just do, so we have slope, which is equal to rise over run. So that is going to be our acceleration over 1 over mass. Okay, now I'm going to show you, you can do this with the variables just the way that they are. I know that I have to get 1 over mass out of the denominator because we can't have 2 fractions. So if I multiply by the reciprocal, multiply by mass over 1, what ends up happening is our slope is actually acceleration times mass. But I'm going to write it like this. Slope is mass times acceleration, which, if you remember, is the equation for force. Okay, so our units here would be kilograms times meters per second squared. And a lot of times you will see that written as kilograms times meters all over seconds squared, which for whatever reason seems to confuse people. I guess it's easier to notice that these are the units for acceleration, these are the units for mass. Well, it turns out that a kilogram times a meter over seconds squared, that is the same thing as a Newton, capital N. So the units for your slope are newtons, and it represents the force. Okay? So the force that was applied. So that answers questions 6 and 7. We know that the units are newtons, which break down into kilograms times meter per second squared, which should make sense because that's mass times acceleration. And then when we do our physics equation, remember in that y equals mx plus b format, so what is on our y-axis? It would be the word acceleration. Okay, that is equal to the slope of our graph, which, bear with me here for a second, I got to switch back over here. So it's kind of hard to see, but the slope of my graph is right here. It's 0.48. So I'm going to come back over here, and I'm going to plug in 0.48 newtons. Okay, this is y equals m, the slope, times x, which in this case is 1 over mass, plus our y-intercept, which my y-intercept is 0.517. 0.517. So 0.517. And then the units for my y-intercept would be the same units as the y-axis, which in this case would be meters per second squared. Okay, so this right here is your physics equation. Okay, so if you need to, pause that and go ahead and do yours. I'm going to go ahead and erase this, and we're going to move on. Okay, so the next part is going to be on the changing force tab, and on the instructions, that would be part 2. So you'll need to go to that second tab. And then basically the difference here is in the first part, you were changing the mass, the total mass, and you were leaving the force the same. So that hanging mass was always pulling with it was the same hanging mass, so the same force that's pulling on it. But the total mass of the system was changing because you were changing the hover puck. Now we are going to leave the total mass of the system the same. Even though we are going to change the mass of the hanging mass, we will counter that with a change in the hover puck mass as well. So you'll want to run through that real quick and then maybe come back to the video, and I'm going to go through that. So this time we've been changing the hanging mass, which is changing the force. So once you have your times over here, we'll need that for acceleration again. The force is really asking you for the weight of the hanging mass. So since the mass is 0.1 kilograms, remember that weight, Fg, is equal to mass times the acceleration due to gravity. So all that we have to do is multiply the mass by 10 meters per second squared. Okay, so when we come over here, all you have to do is enter an equation equals, click on the mass, multiply that by the number 10. You hit enter and you drag it down. That gives you the force that is pulling on the hover puck. Okay. For the acceleration, we're going to enter that same equation that we used before. It's going to be 2 divided by the time squared. If you need a refresher on that, go back to the first part of the lab where I explained that equation and why we use it. Drag that down, and now we've got all of our acceleration. Okay, so it asks us to make an acceleration versus force graph. So that's right here, using Google Sheets, plot an acceleration versus force graph. So that means we want force to come first. That'll be on our x-axis. We'll go ahead and chart that out. I'm going to go ahead and get rid of this for us. And you can see this already looks linear. So I'm just going to go through our checklist. These boxes, it's a scatter plot, customize, check our horizontal axis. These are not checked. We're good there. The title, let's go ahead. The vertical is good. The horizontal is good. The title, however, it's just too busy with all the units in there. Let's get rid of that. And once you've done that, you can go to series. You can go to series, and this already looks linear, so we'll put a trend line on there. We're going to get that r squared on there, which is beautiful, and use the equation. So now we've got a nice looking graph. Okay, and we'll use this for our analysis. So going back to the lab report, the shape of this graph is a line, and it is linear for the relationship. We added the equation, units of our slope. Okay, so let me scroll down again here. We're going to do the same thing that we did before in looking at these three. So for our graph, remember, we did acceleration versus force. Okay, so if we try to do what we did before for the slope, the rise over the run, it would be acceleration over force. Well, that doesn't really do a whole lot for us, because remember the equation is F equals ma, right? And if you were trying to isolate mass, it would be force divided by acceleration, which is the opposite of that. Okay, so let's go ahead and put the units in and see if this makes sense. We've got meters per second squared over, and I'm going to break newtons down into kilograms times meters over seconds squared. Okay, instead of writing out a whole newton. Now again, we want to get this out of the denominator, so let's multiply by the reciprocal, which would be seconds squared over kilograms times meters. This all cancels out, and then we're going to do the same thing up here. Seconds squared over kilograms times meters. Well, look at what happens. Cancels, the meters cancel, and all we're left with is kilograms in the denominator, which would be 1 over kilograms. Okay, well, that is 1 over mass. So the units of your slope are 1 over kilograms. Your slope represents 1 divided by the mass. And then if we go into our physics equation, we'll do the same thing that we did before. We're going to write out acceleration That's what's on our y-axis. That is equal to our slope, which we need to go back to our graph for that. And the slope of our graph is right here, 0.88. Okay, and let's go ahead and look at the y-intercept too. It is really, really small. It's in between 0 and 1, so I'm just going to write it in as 0. But our slope is 0.88. So I'm going to write in 0.88, which is in 1 over kilograms. That's being multiplied by whatever's on our x-axis, which in this case is force. Okay. Plus 0 meters per second squared, because our y-intercept was so small. Okay, so this is your physics equation here. Okay. So once again, I'm going to erase this, so if you need to pause the video, go ahead. But we're going to get rid of this. Okay, and now for the final analysis, it says, using the results in both parts of the lab, write an equation below for the relationship between force, mass, and acceleration. So we've already been talking about this. You've already seen it. It's actually on the screen right now, up in that top left corner, but it is F equals the force equals the mass times the acceleration, or I more commonly like to look at this rearranged for acceleration, which is that really we're talking about a net force here. So the net force is equal to mass times acceleration, and acceleration is equal to a net force divided by mass. And that is the whole point of the lab. Okay, so just understanding the units, especially on that first graph, I think are really important up here. When we make that physics equation and its acceleration is equal to your slope, which is force times 1 over mass, if we kind of go back to that, I think it's going to help you understand where that equation comes from. Remember, we did acceleration is equal to the slope, which was the force, times the x-axis, which was 1 over mass. And then the y-intercept, really we should have started with 0, 0 as our points, and so that wouldn't matter. But think about this. This turns into acceleration is equal to force over mass. Well, there it is right there. So that's really important. Obviously want you to get comfortable with this equation, but there is your virtual lab going over force, mass, and acceleration.